In this tutorial, we will be discussing how to draw Lewis dot structures. Electrons surrounding the nucleus can be classified as either core electrons, which are the inner electrons, or valence electrons, which are the outer electrons. The valence electrons are the ones who are actually reacting. So for instance, if we look at boron, in the first energy level we have 1s2. That would be your inner electron or your core electrons. 2s2, 2p1, because they're in the second energy level, are going to be your valence electrons. So 2s1, 2p1. Bromine has the electron configuration of 3d10, 4s2, 4p5. Because 4s are bigger than the furthest out, that is where our valence electrons are. The distribution of valence electrons is depicted with Lewis electron dot structures. So the valence electrons become the dots. Valence electrons are distributed as shared or bonding pairs, or unshared or lone pairs. So these here are unshared pairs. They're also called lone pairs. You'll see them called both. Where this one is your shared pair or your bonding pair of electrons. Once again, you'll call them both. They're called shared because they're being shared between the hydrogen and the chlorine here. They're being shared between two atoms. They're bonding those two atoms together. The focus is on how the atoms bond to the center atom. According to the Lewis theory, when atoms bond, they tend to gain, lose, or share electrons to result in a full shell or a noble gas configuration, giving it an octet. Hydrogen has a duet because it's most like helium. It only has one electron, and so therefore 1s2 is the maximum that can go into that first energy level. Atoms can achieve the full shell look by transfer of electrons between each other. Ionic bonding is the transfer of electrons between atoms. So the metal gives up its electron to the non-metal, causing a cation and an anion. Cations are positive while anions are negative. The attractions between the ions and are strong and dependent on the size of the cation and anion forming the bond. The stronger the attraction, the higher the melting point. This is true with the covalent bonding as well. Atoms can achieve an octet of valence electrons by sharing instead of taking and giving their valence electrons in their other atoms. So ionic compounds, we have one atom that takes and one atom that gives, whereas with covalent, they're sharing the electrons. The shared electrons would then count towards each atom's octet. Remember, covalent is sharing. Now when it comes to predicting melting and boiling points, the attractions between atoms are directional. This means that there's a specific location for them. The shared electrons are most stable between the bonding atoms. Lewis theory predicts covalently bonded compounds will be found as individual molecules rather than an array like an ionic compound. So they're more like sets. Since Lewis theory predicts the melting and boiling points of molecular compounds should be relatively low. It involves the breaking of the attractions between the molecules, but not the bonds themselves. So we're breaking up the interactions. The covalent bonds are strong, but the attractions between them are fairly weak. Alright, so let's talk about how we actually determine the Lewis dot structure. The very first thing you want to do is count how many valence electrons you have. So you do this by looking at the periodic table from left to right. Carbon, for instance, 1, 2, 3, 4, here's carbon, has 4 valence electrons. Let's look at NH3. Nitrogen's right here. It's in the 5th row. So that means nitrogen has 5 electrons. Hydrogen is right here. It has 1. Because there's 3 of them here, is 1 times 3. So we have 5 plus 3 is equal to a total of 8 electrons. Arrange the atoms in the most electropositive, or in other words, the least electronegative atom in the center. Hydrogen is never, ever, ever going to be the central atom. Keep that in mind. So here we have H3. The hydrogen will not be in the middle. So here's nitrogen. Once again, there is 5 electrons here and 3 times 1 here. So we have a total of 8 electrons. Since hydrogen won't be in the middle, we're automatically going to put nitrogen in the middle. Then we're going to put hydrogen on each side, just like this. So let's draw that again on this page. Draw a single bond between each atom in the central atom. Remove the electrons used to form the single bonds from the total number of valence electrons. Remember, each line is a total of 2 electrons. So if we originally had 8 electrons, we have 2, 4, 6 electrons used, we have a total of 2 electrons left. Place pairs of electrons around the peripheral atoms until the octet is reached. Remove the electrons used in this step for the total valence electron count. Now, I said before, hydrogen will never be an octet because it will be a duet. That's the exception. So, we don't have any one more here to fill up. So let's draw this again. Make sure we're all on the same page. We started off with 8 electrons. We used 6. So we have a total of 2 electrons left. If any valence electrons are left, place those electrons around the central atom until the octet is reached. So I have 2 electrons left. So I'm going to place them on nitrogen. Remove the electrons used from this step from the total valence electrons. So I actually ran out of electrons at this point. Check for the octet for each atom. Note, hydrogen will never reach an octet. If octet is satisfied for all atoms, you're done. So, hydrogen, we have a duet because we have 2 electrons. Remember, each line means 2. Hydrogen here has 2 electrons, so it has a duet. Hydrogen here has a duet. Now let's look at nitrogen. Remember, you count those lines twice. So we have 2 for this line, 4, 6, and then these 2 electrons up here for a total of 8. So nitrogen is also an octet. Alright, so some exceptions to the octet rule. Hydrogen, lithium, beryllium, and boron attain an electron configuration like helium. He has 2 valence electrons, a duet. Lithium loses 1 valence electron to accomplish this. Hydrogen shares or gains 1 electron. Sometimes it even gives up an electron to have no electrons whatsoever. Beryllium loses 2 electrons to become like beryllium 2+, though it commonly shares its 2 electrons in covalent bonds, resulting in 4 valence electrons. And boron loses 3 electrons to become a boron 3+, though it commonly shares its electrons in covalent bonds, resulting in 6 valence electrons. These are the exceptions. The most common one you will have to experience would be the hydrogen. There are also other exceptions for things that are bigger. Expanded octets for elements below the third period. So as we're looking on the periodic table, the third row down, below that commonly have a larger than an octet using empty valence d orbitals. Alright, so let's try this. We have H and F. We don't have to worry about a central atom because of the fact that there's only two elements. Alright, so we have hydrogen and fluorine. Hydrogen has 1 electron, and fluorine has 2, 3, 4, 5, 6, 7 electrons, for a total of 8. So we have H and F are our elements. Link them together with a bond. Hydrogen now fulfills its duet because it has 2 electrons from that line. So we're going to put the remaining electrons on fluorine. So we have 2 electrons used up in that line. That means I have 6 electrons left. 1, 2, 3, 4, 5, 6. And you're done. Let's try this one. Carbon and chlorine. Here's chlorine, here's carbon. 1, 2, 3, 4, 5, 6, 7. Carbon has 4, chlorine has 7, but there's 4 of them. So 7 times 4 is 28, plus another 4 from carbon is 32. Now let's compare them. We actually do have a central atom here because we have more than 2 atoms. So we have carbon and chlorine. Carbon is further away from fluorine, meaning that it's going to be less electronegative. So carbon is going to be in the middle. We're going to put the chlorines all around it. 1, 2, 3, 4 chlorines. The next thing we're going to do is draw lines from the central atom to the peripheral atoms. Here, 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 and here. Let's count how many electrons we've used at this point. 2, 4, 6, 8. So we've used up 8 electrons. That brings us down to 24 electrons left. Alright, so now we're going to put them on the peripheral atoms first. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 22, 23, 24. And that brings us to 0 electrons left. So there is none for the central atom. Let's look at our octet rule. For the chlorine on the left, we have 1, 2, 4, 6, 8. For the top one, 2, 4, 6, 8. For the right, 2, 4, 6, 8. And for the bottom, 2, 4, 6, 8. So all the chlorines have 8 electrons. Now let's take a look at that carbon. We count the bond, and for every bond we have 2 electrons. So 2, 4, 6, 8. So it meets the octet for every single atom here. I'm going to redraw just so it looks a little better. And there is your Lewis structure of carbon tetrachloride. Let's try another one, H2S. Here's hydrogen, and here's sulfur. You will have a central atom here because we have more than 2 atoms. But because hydrogen is never the central atom, we automatically know that sulfur will be. Alright, let's figure out how many electrons we have. 1 for hydrogen, so 2 times 1 because of the 2 here. And sulfur, 2, 3, 4, 5, 6. So now we have a total of 8 electrons. So we have sulfur. We're going to put a hydrogen on both sides. Now we're going to link them with bonds. So far we have 2 bonds from this electron, or 2 electrons from this bond, and 2 electrons from that bond, for a total of 4 electrons. We're going to subtract that out to make 4. Hydrogen will just form a duet, not an octet. So we're satisfied with hydrogen now. Now we have 4 electrons, so we're going to put them on sulfur. 1, 2, 3, 4. Double check the octet. We already said we're satisfied with hydrogen. Let's look at sulfur. 2 for this line, 2 for this line, so that's 4, 5, 6, 7, 8. We're going to do one last practice one. We have carbon, and we have hydrogen. We said that hydrogen will never be in the middle. So in order to make this work, we have 2 carbons here. They're both going to be in the middle. 1, 2, 3, 4. There's 2 times 4 is equal to 8. Hydrogen is 1. 6 times 1 is 6. So 8 plus 6 is 14 electrons total. I said that carbon's going to be in the middle of both of them. Now we need to put the hydrogens around it. And we need to link the central atom to the peripheral atoms. Now let's check how many electrons we've used. 2, 4, 6, 8, 10, 12, 14. We've actually used all 14 of our electrons at this point. Let's double check the octet. Hydrogen will only be a duet. So hydrogen has 2 here, 2 here, 2 here, 2 here, 2, and 2. So we're okay with hydrogen. So let's take a look at carbons. 2, 4, 6, 8. On the other carbon, 2, 4, 6, 8. So we're good. That is our final structure. And that's how you draw Lewis dot structures.